Okay. So steady state scalar transport, we look at scalar transport in static media. So there is no velocity. These are quiescent systems, and we look at heat and mass transport. So let's look at a very easy problem that you all can solve, but not using shell balance. You have a, let's say, a medium, some sort of liquid medium, on which one side you have some concentration of some solute, let's say 100 millimolar, and the other side you have 50 millimolar. Steady state concentration map or profile, as you call it. It will be a function of just x. This is x equal to 0, this is x equal to L. How will you solve it? First thing, you have to look at what governs the system. What equations governs the system? The diffusion equation, which is right. There is no reaction within the domain. Let's take that easy case. Without reaction. So what boundary conditions do you have? Value is specified of the variable, which means Dirichlet. And you have this plus 0, and on the left hand side there is this equation you will apply here with the governing with the boundary conditions. How many boundary conditions do you need to close this problem? 2 and 1 in time, but I am asking you steady state. So this is the equation that governs it while the system is attaining steady state. And once it is done, when it has taken that shape, then you can let go of this term. So usually we say that we wait until infinity, t very long time, t tending to infinity. Now, as engineers, this will bother you. What is infinity? Do we really need to wait for infinity? What is the practical time we need to wait so that we can neglect this? You must be wondering, because this is the fundamental equation, but we are removing one fundamental part of a fundamental equation. There must be a strong reason for that. For now, let's assume it's a very long time. We'll estimate what this time is, hopefully in this class today. Okay. So this is your equation equal to 0. Okay. What is the solution to this? C is equal to C1x plus C2. Already you know that the profile is going to be linear because the double derivative is 0. So you might as well can 100 to 50 just plot a line. No need to even find the solution, but fine. You find C1, C2 using the boundary conditions. So let's apply boundary condition. Let's say boundary condition 1, C at x equal to 0 is 100. 100. So this is equal to 0 plus C2. So C2 is 100, we know. Okay, fine. Boundary condition 2, C at x equals to L is 50. C1 L plus C2. C2 is 100. So C1 is minus 50 by L. So C is equal to, this is our solution. I need different chalk today. Hundred minus 50x by L. Yes, easy, right? It's a decreasing function, therefore as x increases, you'll get this. Now, a general rule of thumb is that whenever you get a solution, you would want to make sure it satisfies the governing equation and boundary conditions. This is easy, so it will be very quick. You take the double derivative of this, is it 0? So governing equation is satisfied. Boundary condition 1, x equals to 0, c is equal to 100, satisfied. Boundary condition 2, x equals to L, 100 minus 50, 50. Satisfied. Okay. Let's move on to the serious example. I mean, this is also not so serious, but whatever. Question 2. What if in the same example, I added volumetric reaction? Let's say there is some zeroth order reaction. Volumetric reaction. So, as soon as I say volumetric reaction, you should remember that this is happening within the volume of the domain. So, it is in the domain. It is within the domain. This is very important. That if there is something happening within the domain, use it in your governing equations. So, this should show up in your governing equation. Okay. So, what will you have at steady state? Let the left hand side be 0. You have d square c by dx square plus reaction term or the generation term. What is this? K, and this is, let's say, source. So K is being generated. You can take K being depleted also. Okay. So if K is greater than 0, we will take this. So this means that it is generation of C. If it was depletion, then I would take this depletion of C. So I'll change the sign here instead of making it positive negative. Okay, K is some quantity which is always positive. Generation of C plus K. This. Let's go with the generation part. D square C by dx square is equal to minus K. K is some positive number. Took on the other side. Before we solve, can you tell me how will the profile look? Will it look linear? It will not look linear. Why? Because there is curvature, finite curvature in the profile. So as long as this is non-zero, there will be some non-linearity. So immediately you know that non-linear profile will set up. Okay, now will it look like this or will it look like this? Concave up, down. So this was the steady state profile last time. This won't be true this time. So will it be like this or will it be like this? Top one, bottom one. Top one, right? But we have to find it. Again, how to find it? Very easy. C is equal to minus K x square by 2. Oh, I made a mistake. D should be added. C is equal to minus Kx square by 2D plus C1x plus C2. Yes? Apply boundary conditions. So now this time you apply very quickly. Someone got it? But can you get it? Shall we move on? Easy, right? Okay, let's move on. So last example. So consider that you have your friend brought. Please. Your friend brought an iron to iron the clothes. Some Bajaj iron. Let me draw it. I don't know how it looks. Okay, this is how the iron is, and this is the resistance heating or the heating coil. Yes or no? So the power goes into this resistance heater and generates heat, electric power. And this is, let's say, some metal slab, some stainless steel or some sort of iron alloy. This is your metal. Now heat is diffusing through this, and you're going to iron your clothes, and it will impart that heat to your clothes. Now this is in a box which has some specifications. I'll let you know what those are. But your query is that will this iron burn my shirt at steady state? Okay, my shirt burns at any temperature above 500 degrees Celsius instantly. So you let the iron be at steady state, let the temperature profile develop or whatever. You have to estimate whether the temperature is less or more than 500. Based on that, you give your recommendation ki you can iron or not. Now, what all information will you need to model this system? First thing, what you'll do? What did we do here? Governing equation. Very good. What is the equation governing this? Let's write down the entire one and then take out the terms. So you have rho Cp dou T by dou T is equal to K del square T by del X square. This is one dimensional plus E gen dot. Now I'll take rho Cp on the other side, make this thermal diffusivity, and this is rho Cp. Okay. Now I'm asking steady state. So let's say you wait for long enough time. So this is equal to 0. Okay. Now what? Should we keep this or not? The iron has a power rating. So let's say it is of 1200 watts. So there is power being provided to the iron. So will we keep this or not? How many say we remove it? How many say we keep it? Why do you say we keep it? My friends at the back, yes, with the specs. Is generating regularly, right? Is this generation within the domain? What is the domain? Right? That would be the question. This metal is the domain. The heat is generated in the heating coil, which is outside the domain. So power is being provided, but through the domain or through the boundary? Through the boundary, right? So the profile is going to be linear or non-linear? Steady state profile? Steady state profile will be linear. But you need to provide the boundary conditions to close the system. What boundary conditions will you use? So I combined a lot of boundary conditions in the last class, right? So I'm just bringing these examples for you to refresh and see how to use them. At X, so you have, what is your domain? This metal. Yes. What is at X equals to 0 and what is at X equals to L? What is at X equals to 0? The coil, but what is it? Yes, you're right. There is a coil giving heat, but what is it? What will you use here? What Neumann, Dirichlet, Robin mix, whatever. Which one? 3 types of boundary conditions we did, right? Is this Dirichlet? Is a temperature being provided at this? Temperature is not provided. What is provided? Some power is provided. Hmm? So what kind of boundary condition? Huh? Newman? Newman, what is Newman boundary condition? Flux is provided. Is flux provided? How come? This is power, right? What is another heat transfer quantity which has units of watts? Q or Q dot, right? So is Q dot provided at x equals to 0? Okay, so let's write down boundary condition 1. Q dot at x equals to 0 is, let's call it power for now, because I don't want you to do any calculation as of now. Let's call it P, and let's say it's known. This is P, but is this useful right now? How will you use it here? Everything is temperature. This is Q dot. So what do you need to do? Convert it using Fourier's law into temperature. What should I write then? Minus K A, right? It's not flux. dt by dx at x equals to 0 is equal to some power. If I had changed the problem to not this iron but some sort of a coolant which absorbs heat at a typical rate, then what would change here? Sign would change, right? The flow of heat would be in the opposite direction. So here it's positive, meaning it's towards the x. So you have to keep that in mind. Okay. So we can convert this and write. We can write it. Dou t by dou x is equal to p by minus p by k. And AC, let me call it for cross section. What about second boundary condition? Second boundary condition. Dirichlet boundary condition, temperature less than 500. No. Look at the system physically. You don't know whether temperature is 500 or not. And I don't know how can you apply boundary condition less than 500 in the boundary condition. So you could do it in the other way. I understand what you mean, but we'll discuss that later. But look at this system. You have a metal, a power B is being provided. This temperature is unknown, TL. You have to find TL. So you cannot give it as boundary condition. Yes. So this iron, you've kept it, right? It's open to ambient, right? Mixed boundary condition. So what should I write? That the flux outside is Q dot at x equals to L is what is it? See, there is a flux which means here just left to this boundary, just before it exits the body. That is Q dot. You can write it using your Fourier's law. What it should be equal to? Conductive Q. Convective, na? Conductive to we'll have here. HA. Because otherwise, if it's not equal, then there will be some build up on the interface. Right? So whatever has come until this boundary has to leave from the other side. So this is Q dot HA again HAC. So this AC and this AC will be same in this case. Rectangular geometry. Cross section and the outside is same. What should it be? T at lower coordinate minus T at higher coordinate. Why I'm saying all this? Because if I have flipped it, it might cause some confusion. So TL minus T infinity. T at x equals to L minus T infinity. Okay, now it's very easy to solve. It will be a linear profile. Same C1x plus C2. I'll just directly give you the answer and you can find this at uh, your hostels. So T will be again C1x plus C2, same old. What you will get in the end is T infinity plus power by area L minus x by k plus 1 by h. Okay, and this is AC. This is what you will get. You have to do this via homework. Now, you could use your calculators to do some calculations, but again, I will again leave that to homework. And what you should find is that indeed it is beyond 500. So it will indeed burn TL. What value it is? I think it's 520. You can find it. So you can solve it. Everyone can solve it here. I'm pretty sure. So I'll not waste your time. But now I want to ask a subsequent question. Can I move forward? I don't need to show this calculation, right? Okay. What would you do now as a, I mean, you have the system with you, you purchased it already. And now, again, but sorry. This will not come 500, this will be only true for the given values. Sorry about that. 300 I should give you, centimeter square. T infinity is 20 degrees Celsius. H is 80 watt per meter square Kelvin or Celsius. L is 0.5 centimeter and K, let it be 200 watt per meter square Kelvin. Okay. So for these specifications, this is what is given to you. This is in your box. This iron is with you. These are the specs. You can't change them. You already purchased it. And you find that this comes out to be 520. Let me, that's right. You verify this is correct or not. Now, what would you do? Would you return? Will not return because refund may come or not, right? So, what do we do with this object? What can you do physically? Huh? Another surface, so another shirt. This, but that shirt, bechara, will not get ironed and never it will get ironed. So what? Can you change K? No. It's a material property. L is there. Either you can add an insulation, let's say a paper laga ke you can do something, but that's unreliable because it can burn. H can you change? Pani chidak ke. That is a very difficult problem, so I'll solve it later. But can you change H simply? Huh? How can you change H? What is H? How did it enter the problem, this sneaky H? Through this, right? Through this, right? When we said conduction is equal to convection, means something that is outside the device should be in our control. How can we change H? Pankha chala ke. So you increase the fan speed, your heat transfer coefficient will increase, right? That's the reason when you, when you go on bike in winter days in the morning, you tell your friend, "अरे धीरे चलाओ थोड़ा, ठंड लग रही है." क्यों? Temperature तो उतना ही है. Heat transfer coefficient is different, right? So, and then let me tell you then what happens if you keep increasing speed like crazy? Keep increasing it, so that H tends to infinity. Then what will happen to the temperature profile? This term will go to 0. What will happen to TL? Check. See, write down, see if it is equal to T infinity. See if TL becomes equal to T infinity, or T ambient if H is infinity? Just check it. Why you are saying yes? Not mathematically, physically. There is no barrier between the end of this domain and the ambient. No heat transfer barrier. We are saying as soon as the heat leaves this domain, it just gets taken away. So the temperature of the ambient should be at the edge of this. And then also you'll see it in maths. Okay. All right. Let's now solve a more involved problem. Okay. So suppose that there is a reactor. And in a reactor there is a stagnant film on the periphery of the reactor. So to be exact, falling film reactor, let me say. And on the edges there is this liquid film being deposited, and it's moving at a very slow pace. It's moving so slow that you can consider it static in this example. So let me just take this out for convenience, and let me consider a geometry around which there is a film, liquid film. Okay, and in this film my reactant A is diffusing in from the ambient. Ambient meaning, I mean, this is within the reactor, there is some A in the gaseous phase, and it's coming in here and sort of entering into this system. You can again imagine that for at this boundary CA is equal to CA naught, some constant value. Okay, so some constant value will be given to you, which is in the ambient also, meaning that the mass transfer coefficient is really high, just like what we discussed. Okay, it's entering this, but there is very little gradient in the ambient. Now as soon as it enters, A transforms to B. As soon as it enters, it reacts. Again, is the reaction happening in the domain or on the boundary? In the domain. And as soon as B is formed, B is subsequently taken away and ensured CB equal to 0, meaning some reaction is happening here in the gaseous phase where B turns to, let's say, some C. Okay, but we are not concerned about C here. So just consider the system of A and B. And to start off, we'll just consider A. And the task has been given to you to find out whether what thickness of this film is actually being used in the reaction. Let's say this C is a very prized product. So we have to see how much B is formed. For that, we have to see how much A is being utilized. And how much this film. So because this film acts as a medium for reaction, right? So we have to find the region which is actively participating in the reaction and which region is more or less it's dormant because A didn't reach there only. So you can imagine this, right? If A is entering this, if the film is very thick, or let's say the reaction is very fast, then it will get consumed very quickly here, and the quantity of A or the concentration of A will be very less as soon as it reaches here, and so A is not present here. So this is being wasted in some sense. So you have to estimate what is the thickness of this region. Now you may think it will depend on K, it will depend on D, it will depend on the thickness. Fine, but how can you? I mean, this is a physical object. But can you use your governing equations to find a solution to this problem? Can we start? So you have a stagnant film in reactor setup. A gives B and the reaction is minus kCa. Again, K is greater than 0. So A is being consumed. So reaction is minus kCa. So when I write my equation, it will be that minus sign will come. So, and we'll only focus on Ca. So I'll just take for convenience C equal to C and write down my equation. And we are focusing on steady state profile. So let me take this as 0 is equal to dou square or d square C by dx square. What, plus or minus? Minus, right? Minus Kc. First order reaction. D, yes. I keep forgetting this. Thank you. Now what do? We have to write down the boundary conditions also. C at, what is the boundary condition at x equal to 0? Dirichlet-Neumann mixed. This is a solid surface which is not allowing A to pass. So it is flux of A through this is 0, no flux. So I should write this J is equal to 0. You can write diffusive flux. Then I can simply write this as dou C by dou x equals to 0, right? At x equals to 0. What about C at x equals to L? Is it a Dirichlet? C not, right? So we know that quantity or concentration. Now one can solve this problem. Let's solve it. So let me take it to the other side, and you have d square C by dx square is equal to kC by d. Yes? How will you solve it? Will this be linear or non-linear? Non-linear, right? But how will we solve this? Can we directly integrate it? We can't directly do it like the last example, but you have to assume. So this is like d square y by dx square is equal to some sort of d y, right? You assume y is equal to e to the power minus mx or something. Sorry. Okay. So, will this admit an exponential solution? So you can imagine c is equal to e to the power minus mx. So what do you get? Double derivative plus m square to the power minus mx. So I substitute this here is equal to k by d e to the power minus mx. Yes, this is cancelled. M is what? Plus minus root k by d. So the solution is c is equal to c1 e to the power minus, or maybe plus first, k by d plus c2 minus x k by d. Yes or no? Now, can I write this in sin h cos h terms? Hyperbolic form. Just that it's more convenient. Huh? For those who don't remember, I'll just write it here. Sin h x is e to the power x minus e to the power minus x by 2. Cos h x is equal to e to the power x plus e to the power minus x by 2. So if you just combine them, you can just write that e to the power x is equal to sin h x plus cos h x, and e to the power minus x is sin h x minus cos h x Okay, so basically you substitute this, you know these definitions, right? So you twist them around, find this, substitute it here, and then shuffle them and combine the terms. What you'll get is C is equal to A sin h x root k by d plus B cos h x root k by d. Okay. What is A and B? A is equal to some combination of C1, C2. So I've shuffled them around and they are, I think one is C1 plus C2 and B is C1 minus C2. Okay, now what do we do? Apply boundary conditions to get A and B. Okay, so what is the boundary condition? This is your BC1. So dou C by dou x at x equals to 0 is 0. Dou C by dou x at x equals to 0, what will it be? A cos h x k by d, but this is 0, right? X is 0, right? Into multiplied by root k by d plus b again root k by d sin h 0. But sin h 0 is 0. You can see it from here also. 1 minus 1, 0. So this is 0. And this is equal to 0 because this is the boundary condition. So you have 0 is equal to a multiplied by something. And this is cos h0. Cos h0 is 1. So you have a is equal to 0. So this guy goes away. Now boundary condition 2. You have Dirichlet condition C naught, huh? So you have C at x equals to L. C at x equals to L is C naught is equal to A is 0, right? B cos h L. Okay, ready. What is B? C naught by this cos h. So my final solution would be C is equal to B is C naught by this. So you get C naught cos h x root k by d divided by cos h f k by d. This is your solution. Now, can you answer the question? What was the question? Initial question. Did you write? Or maybe let me repeat it. Provide a rough estimate of the portion of the film that is actively participating in reaction. In other words, provide the estimate of the region within this film that has A. How will you tell me? So I am only asking for an estimate. So you can give me, let's say 20%, 30%, some rough estimate. Can you give me from this, is there some genius here who can do computations in their mind and tell me? What percentage? So if I give you K and D, and let's say L, you have to plot it and show it, right? Yes, so let's do that. Right now you could analytically solve it, but it was very difficult to probe it just by visual observation. So we plot it and get the answer. What percentage? So we'll plot the profile and we'll see what percentage there is a nice chunk of A. What do you expect the plots to be? So before I show you, can you tell me what you expect? Let's say I do C by C naught versus X. For a given L, K and D, what should be the plot? Your solution should obey the governing equation and the boundary condition. You can substitute it back and see if that governing equation is satisfied or not. That is your homework, which can come in exam. And does it satisfy boundary conditions? That you can tell me right now. What is at X equals to L? C is equal to C naught, so it should be 1. Is it 1? So the plot should be some 1 quantity. Now, as A is diffusing within the domain, right? So this is X equals to L. When it's diffusing in the domain, will it decrease or increase? Decrease. Yes? So it will decrease. Or will it decrease like this? Which one is correct? Again, you have to expect a solution. Anybody can look at a solution and say, "Ha, it should be like that." But thank you. But you have only truly learned if you can expect the solution at least for these simple expressions. Which one should it be? This one or this one? What is the boundary condition at X equals to 0? Huh? Huh? Dou C by dou X is 0, right? Which one is 0? No one is 0. Dou C by dou X, meaning the slope is 0. Means at very near positions, C will not change with X. Meaning it will be a flat line. This is a flat line, right? So this is wrong and this is correct. This is what you should get. Let's see if this is. And because if we are plotting and we don't get what we expect from all our understanding, then our plot should be wrong. If you don't put an expectation, you will just accept whatever junk the simulation is throwing. Okay, entire screen. Start. Okay. Okay, can you see? Okay, so what I've done here is I've made a function. Those who did some small Mathematica session will appreciate it, I guess, or will be able to understand it. How many of you did it? There are 12 people I know. Yes, okay. So, to you guys, it's clear, right? You can define a function. Did we do function defining yet? Okay. So, this is just a function that I've given you there. This is the ratio of the concentration, and I'm giving you a plot with some manipulate function, meaning I can manipulate the value of K, D and L, because those are the only inputs that I can give in that solution. Okay, so let me just take it all the way back. Alright, so this is my, you can see the values at the back. This is my plot. Does it satisfy our expectation? Yes, okay. Now, if I change K, what do you expect? Again, expectation first, the result second. This is your plot. You change K, what do you expect to this will happen to this profile? Huh? It will shift upward. What you are saying, if this happens, and let me draw with another line. If this happens, means what? More C has diffused in, more A has diffused in. That would only be possible if reaction is high or low? Low, right? Okay. So this should be lower. So this is the direction of K that should happen. Let's see if this is true. And also, since I'm here, please tell me if what will happen if D is increased. If diffusion rate of A is faster than the reaction, Meaning in physical terms, your molecule is getting smaller, so it moves very fast. So it will diffuse further. So this should be the direction of increasing D. And again, since I'm here, please tell me also L. What would happen if I increase the film thickness? If I increase the film thickness, let's say instead of 1, I made it 1 point something or 2. So first of all, I'll be starting from here. So it will decrease more, right? Because as it has to cover more distance to come in. So it will never be able to match this value because it will get consumed. Yes or no? Any confusion? Expectation you should understand. If there is any confusion, I can repeat. But once I show you, then it will be spoiled. Repeat करते हैं एक और बार. कौन सा last वाला? If there is more film thickness, meaning there is more barrier to cover. So initially film was this, now you made it this long, and now A is entering, and A will, if it has to reach all the way to this increased thickness, it will get consumed more than it was getting consumed before for the fixed K and D. So it will be lower than this white reference plot. So let me do one by one. K, let's increase K. Yes, if we go K really high, you see that really this entire region is not being used. A just cannot even penetrate at this high level of reaction rates. Okay, let me take it all the way back. If I increase D, my profile is almost flat, meaning reaction is not happening. It's happening at a very low pace compared to diffusion, so it can just come in. If K is 0, what would be the steady state concentration within the film? If K is 0, if there is no reaction, just flat, right? So it's approaching that, so it's consistent. And again, let's go to the length. Again, as the length increases, again you can see that your domain is increasing, right? So what it was before, it will not be able to take the same value, it will get consumed. Okay, so our expectations are matched, but still the answer, we didn't give the answer, right? What is the region? Now the answer is like this is the region, qualitative answer. What you can do further is spend some time, few days or maybe an hour or so, depending on your skills. You find the 99% region, let me track that, or 90% region, and let me see how much region is there. You can do this numerical analysis and you can plot that and show. But again, you have to show that plot versus K, versus D, versus L. So this estimate and the answer that you gave to the question is not very satisfying, right? Or it's a very lengthy answer. We wish if there was a smaller answer to give. So we'll do that now. One can, you can argue also, you can say that, oh, we have just found out that this region delta, let it be delta, and let it be delta by L, meaning this is the, let's say, region thickness divided by the entire region thickness, entire film thickness is proportional to what I find from my plots, K, the region which is being used. So if K increases, you saw, right, this was increasing. Let me do it again. Oh sorry, it was decreasing, sorry, decreasing, right? So but and it was increasing with L and increasing with D. No, sorry, decreasing with L. Yes? D and K and L were in same directions. But you don't know the exponent. Yes? You can say now, I know dimensional analysis, Buckingham Pi theorem. I can just match the dimensions and find what are the exponents. Yes? You can do that. But what will that tell you? That this is some sort of Damkohler number. We'll find it. This will come out to be, this is -1. KL square. Please don't note it, I'll introduce it more formally, but this is some non-dimensional number. But there is another disadvantage of dimensional analysis, meaning it cannot give you with what exponent it will depend on. -1, -3, +1, +2, half, 1 by 3. We covered this, right? So you can still do dimensional analysis and make it compact. Say that this non-dimensional number will emerge and my system will, or my answer will depend on just damn Kohler number, but you still have to do numerical simulations to find that thickness, to find that power, what this overall power be. You can find relative powers, but that overall power will only be revealed from the simulations. So still, there is a need for a better approach, and we'll approach it through non-dimensionalization. So this was all a justification to learn to do non-dimensionalization. Sometimes people call it scaling analysis or normalization. And so there are two advantages that we'll see, is that our solution will become much more compact. We will see non-dimensional numbers naturally emerge. And not only that, non-dimensionalization makes it possible for you to find the answer that I'm asking without even solving the partial differential equation. So you will be able to get the answer just by looking at the governing equation. Let's see. Before I attempt this question, I'll just take a minute or two to tell you what is non-dimensionalization using a simple example. Okay. It's a very long name, so I'll just write ND from now on. So the basic idea behind non-dimensionalization, if I can put it in very informal words and short words, is extractions of dimensions from dependent and independent variables. You will have a governing equation. You have seen governing equations in all the examples that we've solved, 4 examples, right? Every time you started with governing equation. When you say we're going to non-dimensionalize the system, what we mean is that in that governing equation, we'll extract the dimensions out of the dependent variables and the independent variables. Okay, so question 1. So let's say your question 1 that you did, right? And the answer you got. So you had 100 millimolar and then 50 millimolar. What was the equation that you were solving? D square C by dx square is equal to 0 with the boundary condition of C at x equal to 0 is 100, C at x equals to L is equal to 50. So a typical non-dimensionalization would look like that we have to find something to divide this by, divide x this by. There are only 2 variables here, one dependent and one independent. So we have to find something known as the characteristic scales, and we call it CCH and XCH. What I mean by characteristic scales is that, see, the idea is the following: we are going to extract the dimensions out of the system. So we need to find what we are extracting. In terms of length, we'll extract the length out of this x. So what is the characteristic length of the system? So if this is a table, let's say you are studying this equation in this domain, this is of 1 meter. The characteristic length would be the total length, something that we know. So this would be L. And then what you can say is that I'm going to define something known as x bar, a non-dimensional number, that will be x by L, so that my length goes from 0 to 1. L could be now 1 meter, 1 centimeter, 1 micrometer, 1 kilometer, I don't care. X bar goes from, belongs to 0 to 1. So when you are doing simulations or even plotting, you just go from 0 to 1 in your plot and stop worrying about what the unit of L is. So in some sense you become unit free. What do you do with CCH? What is the characteristic concentration? C at this or this? C at 0? How about what is driving this diffusion? The difference between them, right? If it was 100, 100, then it would, there would be any diffusion. So this is difference is the characteristic scale. So this I should call it some sense delta C boundary. Okay, and this is let me call it C1 minus C2. This is C1, C2, and I'm going to define this as, this will be slightly different, C divided by the C1 minus C2, but again, as we said and we agreed on, that concentration difference is driving the diffusion. So there should be a concentration difference that is being divided. Yes? You could take C1. You could take C1. You could reverse it. Do whatever you want. But when you take this, what will be the range of C bar? At x equal to 1, 0 it is 100, C1, this is 1. And at other part this is 0. So again it ranges between 0 to 1. So you see, everything convenient, everything unit free. Now C could be millimolar, micromolar. Okay, you can now substitute this inside it. What to do? This is there, we have to write the non-dimensional version of it. E is equal to C bar into you can do this, and then x is equal to, I'm writing them in the substitutable form. So I defined them like this, x bar is x by L, it has 0 dimensions, no dimensions. C bar has no dimensions. Now in order to substitute, I have to write the old is equal to something into new. And then substitute it. Or what you could do, you could say that I'm going to divide or subtract this by some scalar quantity C2. You could also do that. It doesn't matter because C2 is some number which is, you can take the derivative of it's going to be 0. And you can say that I'm going to divide it by C1 minus C2. Whichever way you prefer. Okay, let's do it the simpler way or gradual way. So you have here I substituted. Will this matter? Will this matter? Some people are on autopilot. This will not matter, right? It is within this, right? So what do you have? Whatever terms you got out, they are, right hand side is 0. So right now it doesn't matter. But this is your, sorry, I am on autopilot. So d square c by dx bar square, this is your non-dimensional equation. It is very, I mean, it's the same as what you had before because right hand side had nothing. But right now it doesn't matter, but in the problem that we'll solve, you had something, right? Reaction term. So something will happen there. Okay, so you have this. Now you can solve it. C bar is equal to C1 x bar plus C2. Apply boundary conditions. Boundary conditions also need to be non-dimensionalized. This is also an important point. Because they are in C, you need boundary conditions in C bar. And they would be C bar at x bar equals to 0 is, please tell me this. This is C1, right? Just substitute that in the definition. So C1 minus this 0, 1, right? X bar equals to 1. Even this will be non-dimensionalized, right? Is equal to 0. If we solve it, it will be 1 minus x bar or something. I mean, already you see it's very compact. All of the dimensions are, what you can do, you can unpack this. You can use the definitions that you've seen here, keep them in mind. Once you get the solution, you can put it back and see if you get the same answer. You will get the same answer. Now this solution, would it change? This non-dimensional solution, not the redimensionalized solution. This will it change with the domain size? If L was 1 meter, 20 meters, no. Will it change with the concentration, absolute values of concentration? So this is advantage number 1 of non-dimensionalizing a system, that your non-dimensional solution. So there will be, I think, 4 or 5 advantages. I'll keep writing them as we encounter in different problems. This is number 1. Is that your system is domain independent and scale independent. Domain bolo, unit bolo, scale bolo.